In this video, we're going to talk about the kinetic molecular theory. When we first started this semester, we talked about the scientific method, and the big difference between laws and theories is that laws basically just tell us what, whereas the theories are explanations for why. And so we're going to use the kinetic molecular theory to explain the ideal gas law. So, as is typical, the laws, because they just tell us what, are often fairly compact, right? The ideal gas law is just PV equals nRT. Right? And the kinetic molecular theory that explains the ideal gas law is a little bit more involved. So depending on the source that you look at, they break up the kinetic molecular theory into a series of postulates. And what we do with the kinetic molecular theory is we use the microscopic behavior of the gas particles to explain the ideal gas law. Now, a lot of the parts of kinetic molecular theory are things that we've kind of talked about already. We're just kind of collecting it together. So I think on our very first slide, in our very first video on gases, we said that gas molecules travel in straight lines and change direction only when they collide with each other or with the walls of the container. Right? And then when we defined an ideal gas, we talked about the fact that the size of the molecules themselves are negligible compared to the size of the container. When we introduce pressure, we talked about this next point. Pressure results from the collision between gas molecules and the walls of the container. This next one was also part of our definition of an ideal gas. Gas molecules exert no forces on each other, and the collisions are completely elastic. That means there are no reactions. And then I think this last piece is an important piece, and this is kind of new. So according to the kinetic molecular theory, the average kinetic energy of the molecules is proportional to the temperature of the gas in Kelvin. So higher temperatures mean the molecules are going to have higher average kinetic energies. Right? And so what we want to do now is look at the gas laws and see how would we explain those with kinetic molecular theory. Right, now I'm not going to go through all of the different possible relationships, but I'm just going to pick a couple to look at, and then I'm going to use some simulations that we used in an earlier video. So first we have Boyles' law, right? And that tells us that pressure is inversely proportional to the volume and vice versa. Right? And of course, when we're dealing with Boyles' law, we need to keep the number of moles and the temperature constant. All right, so we've got our simulation here. Let's fire it up. So we'll inject some gas molecules in here. I won't inject any more gases, so that'll keep the moles constant, and I need to make the temperature a constant. Right, and so then pressure is inversely proportional to the volume. Right, and so, of course, we can see that. Right now, my pressure is at about, 11, almost 12 atmospheres. Right, and when I decrease the volume, the pressure increases. Right, and so how we would explain that with the kinetic molecular theory, the gas molecules are all still moving the same speeds they were before. The kinetic energy didn't change, but now the molecules don't have to travel as far before they strike the walls of the container. And because pressure is due to the molecules striking the walls of the container, the pressure is going to go up. And so that's how we would explain Boyle's law with the kinetic molecular theory. Right, Charles's law tells us that the volume and temperature are directly proportional. And then, of course, we're going to keep the moles and the pressure constant. All right, let's get our system started. And then just a reminder, right, volume and temperature are directly proportional. And so I need to keep the pressure constant. And I'm going to be changing the temperature. And so I want the volume to be able to change. So I'm going to select that pressure, keeping it constant. Right, and so now when I heat up my sample, we can see, right, as the temperature increases, the volume also certainly increases. Right, and so the way we would explain this, when I increase the temperature, the kinetic energy of my molecules increases. Right, so they're speeding up. And so they're striking the walls harder, and because they're moving faster, they're also striking the walls more often. And so in order to keep the pressure constant, the volume has to expand. And by the volume expanding, now the molecules have to travel further, and so they're striking the walls less frequently. So even though they're striking the walls harder, that balances out the fact that they're striking the walls more frequently, allowing the pressure to stay constant. But in order for that to happen, when I increased the temperature, the volume had to increase. All right, Newton's law tells us that pressure and temperature are directly proportional. We'll fire up our animation here. And then just a reminder, right, pressure and temperature are directly proportional. And so let's inject some molecules into our sample. Right, if we're looking at pressure and temperature, I need to keep the volume constant. And so now in this case, we're ready to heat things up. And so right now the pressure is at about 10 atmospheres. When I heat it up, of course, the pressure is going up. And so now, because the volume is constant, right, now the molecules are striking the walls with more force. They're striking them more frequently because they're moving faster. And so they get to the walls more quickly. And so that increase in temperature resulted in a corresponding increase in pressure. And so this is how we would use the kinetic molecular theory to explain the pressure-temperature relationship. All right, so we could do the same thing with all the other gas relationships, and I would encourage you to think about those and play around with the animation. But let's move on and talk about some other things. So we said before that temperature is a measure of the average kinetic energy of the molecules, and different gases, as long as they're at the same temperature, will have the same average kinetic energy. So in order for that to be true, because those molecules are going to have different masses, they must also have to have different velocities. And the analogy I always like to use, imagine we have, right, a really big football player. Right, and he's running up against a really small football player. Right? In order for that collision to be equivalent, they can't be running at the same speed, right? If the big football player and the small football player smash into each other running at the same speed, right, the bigger football player is going to win that collision. And so the only way for that collision to be equal is the smaller player has to be running faster, right? And if he runs fast enough, then he can have an equal kinetic energy to the larger player. And so the same thing is true for gases. If I have samples of gas at the same temperature, they have the same kinetic energy. The only way that can be true is if the lighter molecules are moving faster than the heavier molecules. Before we look at the next slide, I wanted to point out that the temperature is a measure of the average kinetic energy of the molecules. And so not all of the molecules of a given gas are going to be moving with the same kinetic energy or with the same molecular speed. And in fact, if we were to plot out the molecular speed and how many molecules have that molecular speed, we see that they're not all equal. We get a distribution. And so the average of this distribution, we can sort of think about being roughly where the height of the peak is. If I look at the distribution of the velocities of a number of different gases at the same temperature, and so I should point out here, right, these are all at the same temperature, we can see that they don't have the same average molecular velocities, right? And the lighter gases like hydrogen have a much faster average velocity than the heavier gases like the oxygen and the nitrogen. And that's what we would expect based on the kinetic molecular theory. So just because these simulations are cool, And I can't remember if I pointed out, but I want to be sure before I go on to give credit. You can get to these simulations by going to this web page here. And this group has not only simulations related to gases, but they have all kinds of other cool simulations. So check those simulations out if you're interested. All right, so a similar simulation here, but now I can also look at the speeds of my particles on the left-hand side there. So let's get some gases into my system. And so I can change the size of the gases down here, right? I have large molecules and smaller molecules. So we'll put in some heavier ones, put in some smaller ones. And so when you look at the distributions, you can see the same thing. And you can also tell visually, right? Those little red ones are flipping around a lot faster than the heavier blue ones. And we can see that reflected in both the distributions, where on average, the blue ones are moving slower than the red ones. And then they're also computing the average speeds up here. Right now, both of these gases, because they're in the same container, are at the same temperature. If I look at the kinetic energies, because I have a small sample here, they're fluctuating somewhat, but you can see, right, both because both samples of gas are in the same container, they're at the same temperature, and so they have the same average kinetic energies, right? It's just that in order for that to be true, the red ones the lighter ones, the red ones have to be moving faster. All right. The final thing I want to talk about is how the temperature influences the molecular speed, right? And as we would expect, as the temperature increases, the average kinetic energy of the molecules increase. And so then as we increase the temperatures, the average kinetic energy of those molecules also increases. And we can look at that again with, I'm just going to inject in one of the samples. Right? And so we can see the distribution of their molecular speeds over on the left here. Right? And if I heat those up, you can see the average speed there, we're hovering around 1,200 meters per second. Right? When I heat it up, we can see the average speed increasing. And then, the average of the distribution shifts to higher speeds, but it also spreads out, right? There's more variability, right? We've got some of the molecules moving really slow and some moving really fast, but on average, right, it's quite a bit faster. And then if we slow it down by lowering the temperature, we can see the distribution tightens up and the average of the distribution shifts to lower speeds, as we would expect based on the kinetic molecular theory.